All right, welcome guys. So today we're going to be talking about stoichiometry. So if you guys could please follow along on your sheets here, or if you're using this for review later on, just kind of disregard the writing here. But we're going to kind of walk through from a foundational level of how to do stoichiometry and what exactly stoichiometry is and what's its purpose. Why do we even care about it in the first place? So stoichiometry, if we're to break down this word, stoich, okay, stoich stands for the elements that are involved, and metry means to measure. Okay, let me zoom this in a little bit for you. Okay. So we're measuring the elements in a chemical reaction. So our whole purpose in stoichiometry is that it is a process of calculations for switching or comparing different substances. Now, when we're talking about different substances, we're talking about atoms and molecules, so atoms or molecules, I should say, in a chemical reaction. Okay. So we're going to follow our couple rules, kind of similar to a lot of our other processes, while we are trying to solve stoichiometry here. So our rules that we're going to follow. Okay. The first rule is that we need to have moles as our main unit of conversion. So in order to go from one substance to another, we need to have each substance be in moles. So if you remember correctly from first semester, when we talked about what a mole specifically is, a mole tells us the exact number of atoms or molecules. So if you remember, that was the 6.02 times 10 to the 23rd, that really huge number that allows us to be able to measure something that is microscopic, that we can't actually see with our naked eyes. So the second thing that we need to make sure that we do in any of these questions is that we must have a balanced equation. So this was why we spent some time last unit learning how to balance specific equations in order to understand exactly what we need to do when we are doing stoichiometry. Because if we're going from one substance to another, like the activity that we just talked about, we need to have the ratios in the chemical reaction. So a balanced equation with the coefficients in front of it is going to determine the ratio between different parts of a chemical reaction. So a balanced equation shows how the moles, aka the mole ratio, relates to each part of the equation. Okay. So again, the coefficients or those numbers, so coefficients Should be an E right there in case you can't really see. So the coefficients is going to equal the number of moles of each particular substance. So when we're always approaching these questions, we always need to ask the question, how do we start? So we're always going to start with the number of moles given to us in the question. Okay. So we're going to start with our given value, and then we're going to multiply times, which I apologize, my lines are a little squiggly. I'm writing on an uneven surface here. So the number of moles given of a certain substance from the question, because we have this unit up here of our moles of given, we need to have the same given number of moles on the bottom. And that's from BE, the balanced equation. Okay. Now on top of this, we're going to have an unknown number of moles, again from that balanced equation. So this is what we're trying to get to. We're trying to go from moles of our given to moles of our unknown. And remember, we always are going to set these up with whatever unit we have up top on the previous part is going to be the denominator of the next multiplication factor. Okay. And we do that so that we can cancel those two out. All right, so now let's go and look at a couple example problems, and then we'll kind of take this to the next level here. So let's go through the first one together, and then I'll give you guys some time to work through the rest of this. So, and these might look familiar from our stoichiometry cooking and you activity. So these are very similar questions, except we're using an actual chemical formula. All right, so let's see here for this first one. So it's asking how many moles of H2 are needed to react with 3 moles of N2. So I would recommend getting into the habit of listing out the total number of moles that we're given, or any unit for that matter. So here, any value that has a number is our given. So we've got 3 moles of N2, and we're trying to solve for moles of H2. So here's our given, here's our unknown. So we always start with what we're given, so 3 moles of N2. Okay, and we're trying to get to moles of H2. Now, before we proceed, we need to look here and see, is this a balanced equation? So if you look, we've got 2 nitrogen, 2 hydrogen on the reactant side, and then 1 nitrogen and 3 hydrogen on the product side. So if you're still struggling with balancing equations and why I'm going to be putting these coefficients here, we probably need to go back and revisit some of our concepts from last unit. Keep in mind I have posted tutorial videos on Google Classroom to help walk you through that process. Okay, but just for to do this quickly here, so we've got 2 nitrogen on this side, 1 nitrogen on this side. So to balance that out, we put a 2 in front of this compound here. So now we have 2 nitrogen, but that 2 does not only impact the nitrogen, it also impacts the hydrogen there as well. So 2 times 3 gives us a total of 6 hydrogen on this side. If we have 2 hydrogen here, that means that we need to balance that out. So remember, if we have 3 on one side and 2 on the other, the lowest common denominator that they're going to have is going to be 6. So here we put a 3 in front of the H2. So that means that we're going to now have a balanced equation. 2 nitrogen, 6 hydrogen, and then 6 hydrogen here. Okay, so now we have our mole ratios for each of our different substances. So now we've got 3 moles of N2. So remember, whatever unit we have up top needs to be the same unit down below. Moles of N2. Okay. Now we're trying to get to moles of H2. So now we're just going to put our coefficients, the numbers that are in front of each of those different parts. So we've got 1 here, and then we've got 3 here for hydrogen. So to solve for these equations, we multiply everything that's on top and divide by whatever's on the bottom. So here we've got 3 times 3. That'll give us 9. Divided by 1 gives us 9. So our answer here would be 9 moles of H2 because we've canceled out both of those units. So all we're left with is just moles of H2, our last unit that's in the upper right corner. So I'd like you guys to take some time to attempt these other ones down here. So these are just mole to mole conversions. So I'd like you to pause the video at this point and then have a couple minutes to go ahead and work through this here, work through 1B and then 2A and 2B before we go ahead and transition here. So go ahead and try those out. All right, and this is what we should have come up with for these last couple practice questions. So again, we have to identify what we're given, and I'd recommend putting a box around that so you can easily see what that is. And then whatever unit you have up top needs to be the same unit down below. And then you just plug in your conversion factors, which in this case is going to be the mole ratios for each of these balanced equations. So this is what we should have come up with here. Okay, so let's go ahead and now let's kind of add a layer of complexity. So let's say, for example, that we don't have our given in the unit of moles. So if the given is not in moles, we need to convert to moles first. So now what we're going to do that is we are going to use our mole map. Now, this is a resource that you will have at your disposal on any quiz or test, and it's something that we're going to build piece by piece, one thing at a time, periodically as we go through this here. So we're going to be kind of jumping back and forth with this a little bit. So again, this is our mole map here. Now, a couple things to keep in mind, these central boxes. Notice how we kind of have a lot of options before, we have a lot of options after. So the centerpiece is that we are going to be always having to root through moles. So we're going to have a bunch of different units that we're going to use to do stoichiometry. Okay, so again, our couple of rules that we had. Okay, we're going to be switching identities or the type of element, the type of molecule that we're dealing with in the chemical reaction. So again, in order to go from one substance to another, we must be in moles. So all this action on the sides here is going to be to convert to moles in the middle. Now we must use the molar ratio from the balanced equation. Okay, so remember, in the center of this here, we always have our mole values for both our given and then our unknown. So we're going to be routing any of our given values. We're going to be always converting them to moles. Okay, so this is going to be your number that was given to you from the question. And then we're also going to have, on the other side of this, we're going from our given to our unknown number of moles. So that's what we're trying to solve for. Okay. All right. So again, the way that we're always going to plug this in, like we just did in those first couple of questions, is we're always going to have multiplied by your number of given moles. So again, that's what we're starting with. And then on the top of that, you'll have your number of your unknown moles. Okay. So these values came from the balanced equation. And this is essentially what we have talked about before. This is the mole ratio. Okay, so now we've got our centerpiece of our stoichiometry map. Now we're going to start to fill in the outer parts. Now we're just going to start with one, and then we'll go through an example, and then we'll talk through all of the other different conversions here as well. So the first part we're going to talk about is one of the most common ones that we'll use, and that's going from mass to moles. So if we look here, okay, when we're dealing with the mass, our unit is always going to be in grams. So if we want to convert from grams to moles of our given substance, which actually let's just add to the side here that all of these are our given values, and then all of the ones on this side will be our unknowns. Okay. So if we're going from grams to moles, remember from the periodic table, we're going to use the molar mass of that substance. So essentially where we have our conversion factor there is that 1 mole is going to equal a certain mass from the periodic table. So that's their atomic mass underneath each of those here. Okay. So that's for going from mass to moles. So now let's go ahead and look at an example of that. So going back to our examples here, let's look at number 3. So if we look here, we're going from how many moles of chlorine gas can be liberated from the breakdown of 64 grams of gold-3 chloride. And this is our chemical reaction. So let's go ahead and identify what we're given here and what was our unknown, what we're trying to solve for. So here, our given, our numerical value, is going to be 64 grams of gold-3 chloride. So then we're trying to get to moles of chlorine gas. Now, just like we said before, we need to make sure that this is a balanced equation. So let's look at gold. We've got 1 on each side. For chlorine, we've got 3 on this side, 2 on the other. So we know that we need to get both of those to 6 at least. Okay, so we put a 3 here, put a 2 there. That changes gold as well. So that will make us have to change this to 2 gold or AU as well. Okay. All right, so let's go ahead and start to set this up and again reference our stoichiometry map. So here we're trying to go from grams to moles. Okay. So we're given, we always start with whatever we're given. So in this case, 64 grams of AuCl3. Now, if we go back to our conversion factors here, right? So our conversion factor is going to be 1 mole equals the molar mass of, in this case, gold 3 chloride. So if we look at this here, and let me step away for a second, grab a periodic table. All right. So for gold 3 chloride, okay, and our next step, we're going to need to have grams of AuCl3 down here. Because if we remember, what goes up must come down. So we'll have grams of AuCl3 here. And then we're trying to get to moles of AuCl3. Okay. So again, the reason I set that up like this is because this is our conversion factor. And we're going to get this from the periodic table. All right, so now we need to figure out the mass of gold 3 chloride. Okay, so we find gold. Gold's right here. It might be a little tough for you guys to see that, but we've got, for gold, the atomic mass is 196.9666. Okay, so now we're going to add the 3 chlorine. So we've got AuCl3. Chlorine, again, you probably will have a hard time seeing that, has a mass of 35.4532. So notice how I put this in parentheses, because we are going to be multiplying that value times 3, the total number of chlorine atoms that we have in the compound. So that gives us a total mass for gold 3 chloride of 303.326. So we can round that to 303, let's say 0.33. 303.33. Okay. So now we're not done yet. Now we need to go, we're at moles of gold 3 chloride, AuCl3. Now the question is trying to get us to moles of chlorine gas. So we've gone this step. Now we need to go one more. We're going to moles of our unknown. So now all we're going to do is we're just going to add another step here. So again, whatever unit we have up top needs to be the same unit down below. Now notice how I didn't just write a 1 here, because remember, this is going to come from our mole ratios. So this part right here is from the balanced equations. Okay, so we'll look at that in a sec. So we're trying to get to moles of Cl2. Okay, so now we look at the balanced equation. So we've got 2 moles of AuCl3 and 3 moles of Cl2. So now this is where it's really important how we plug this into our calculator, because now we can solve for moles of Cl2. So we're going to set this up as 64 times 3, because that's everything that's on top. And I would recommend hitting enter then, getting an answer, and then we're going to divide by everything that's on the bottom. So when we hit divide, now if we open that parenthesis, we can just put everything that's on the bottom. So 303.33 times 2, because that's multiplying everything that's on the bottom. We close that parenthesis, and now that gives us 0.316, which we can round that to 0.32 moles of Cl2. So again, the way that we set this up, we broke it up into a couple parts. So we went from grams to moles in this first part here. Then we went from moles of our given substance to moles of our unknown substance right here. So now we just plug all that in, and that gives us a final amount in moles of Cl2. All right, so now let's go ahead and add a little bit more to this process, and we're going to fill out a little bit more of our stoichiometry map here. Okay, so if you remember from previously in this course, we've already done some molar conversions. Now we're going to walk back through how to do that, and again, you'll be able to use this sheet to help you, so just lean on this as a tool to help you if you're struggling. So in addition to using the mass, we can also use concentration. We can also use the volume of a liquid. So here, we're going to use the volume. So volume is always going to be in liters. So if it's not in liters, we'll have to convert it to liters of a particular solution. Now, the trick with these ones is that oftentimes these are going to be given in a molarity, in a concentration. So we represent that with an uppercase M. So uppercase M equals molarity. Now, essentially, molarity is just a fancy way of saying the number of moles that you have in a certain volume. And that volume is going to be 1 liter. So it's saying how much of something is dissolved in a liter of that solution. So the way we could rewrite that here, sorry, I'm kind of writing through some of my work here. We're going to go ahead and use this conversion factor. So 1 liter equals whatever the value was for molarity in moles. Okay, so that might sound kind of confusing. So let's go ahead and add that here. Again, it's 1 liter equals whatever the value is that's given in moles. So again, let's go ahead and look at one. Okay, so let's say, for example, we've got 765 milliliters of a 0.5 molar solution of AlCl3 from our previous balanced equation. And we're trying to calculate the number of moles. So here we're given 765 milliliters of a 0.5 molar solution. Okay. And we're trying to calculate the total number of moles of silver chloride in this equation, which actually I apologize. We're using this new balanced equation for this one, not the previous one. So let's go ahead and balance this one out first. So we've got AgNO3, AlCl3, AgCl, and then AlNO33. So let's go ahead and balance this out. So we've got, let's start with nitrate, NO3. We've got 3 on this side. So we need to put 3 on this side. Now that throws off our silver, Ag on each side. So now we put a 3 here. And then this one, we've got 1 aluminum here, 1 aluminum here. Now we have 3 chlorines, so we'll actually just put a 1 right there. Okay. So again, going back to our conversion factor, we need to convert this to moles first if we're going to get to moles of another substance. So we're going to use these conversion factors that we just wrote down. So let me show you what we mean by that. So here we're given 765 milliliters. Now notice how this is not in liters. So our first step is that we need to convert that into liters first. So if we go and convert this here, okay, so this is kind of separate. This is another part here. This is way back from the beginning of the semester. So 1 liter is going to equal 1,000, excuse me, 1,000 milliliters here. Okay. So if we convert that, that's going to give us 0.765 liters. Okay. So now we've got our amount of liters here. So now we can use our conversion factor from our mole map. Okay. So we'll have 0.765 liters. Okay. Okay. And now, we can also include this. This is AlCl3. So remember our conversion factor that we had here is that 1 liter equals whatever that concentration is in moles. So our concentration was 0.5 molar. So what that means is for every liter of AlCl3, we're going to have 0.5 moles of AlCl3. Okay. And now we're going to plug this in very similar to what we did with the last question. So if we've got moles of AlCl3 up here, we'll need moles of AlCl3 here. And we're trying to get to moles of AgCl. Okay. So we go back to our balanced equation. So AlCl3 is going to be 1. AgCl is going to be 3 for the ratio. And now we're going to solve this the exact same way we did before. Multiply everything that's on top, divide by everything that's on the bottom here. So we'll do 0.765 times 0.5 times 3. Hit enter. And then we're going to go ahead and divide that by 1 times 1, which would essentially be the same thing. So you actually don't need to plug that in. I will just for posterity's sake. So that gives us 1.148, which we can round that to 1.15 moles of AgCl. Okay. So now, we've kind of started to tackle the first side here of the, what happens when you're given a value that is not in moles. Now we're going to transition and look at that from the other side and say, okay, if we are unknown for these values, how will we go ahead and solve for those? So I would like us to go through some practice with this here first. Let's get the hang of a couple of these questions first. We'll take a little breather, and then we'll come back and look at the other side, and then also we'll start filling in some of these other given values. Okay, so now we're going to be tackling the question of, okay, what happens when we're trying to solve for an unknown in a unit that's not just moles? So basically, if we get to this point, but then we need to keep going to the other side here. Now, what's actually kind of cool about this is that both sides of this, you might notice, are mirrors of each other. So if we want to go from, let's say, grams to given moles, and then from given moles to unknown moles, and then let's say back to grams, okay, we can absolutely do that. And the process is going to be the exact same. And again, we just need to let the units drive our setup. So here, we're going to use our molar mass again to get to our final unit of grams, or the mass of our unknown value here. So again, that's going to be 1 mole equals whatever the amount in grams are. And again, that's going to be from the periodic table. Okay. So let's go ahead and just add a little bit more to this. So Okay. So if you're trying to solve for an unknown that isn't in moles, then we're going to convert to the final unit. And again, we're just going to be using the mole map. Which, spoiler alert, you're going to have two options. So if you're trying to solve for a volume of something, or if you're trying to solve for a mass, that's when we're going to do this step here. Okay? All right, so let's say, for example here, that we wanted to, given this equation, we wanted to start with 30 grams of potassium iodide, and we wanted to calculate the mass of lead 2 iodide. So same thing as before, we need to balance this equation. So if we've got 2 nitrates here, we need 2 nitrates here. If we have 2 iodine here, we need 2 iodine here. Now if we look, iodine 2 on each side, potassium 2 on each side, lead 1 on each side, and then nitrate 2 on each side. So now that is our balanced equation. Okay. So if we go and look at this now, let's go ahead and start setting this up. So again, we always start with what we're given. So 30.0 grams of Ki, potassium iodide. Now, no matter what, before we even look at our stoichiometry map, we should be starting to see that, okay, if I have grams of Ki up here, I need grams of Ki down here. Okay. So again, we just did this step right here, going from grams to moles of our given substance. So we'll need to have moles of Ki here. Okay. So again, the conversion factor that we're plugging in there is that 1 mole equals whatever the mass is from the periodic table. Okay. So we've got Ki here, potassium right here, iodine right here. So potassium has a mass of, I know you guys probably can't see it, maybe look at your own periodic tables. That's going to be 39.09831 plus iodine is 126.9045. So that gives us 166.003. So we can just round that to 166.0 grams. Okay. So now we're right here. We're on this little island here. Now we need to get from given moles to unknown moles. So again, same thing. If we're not at our destination yet, whatever unit you have up top needs to be the same unit down below. And then we're trying to get to PbI2. So we can't go straight from moles of Ki to grams of PbI2. Oops, sorry, that should be a lowercase b. Okay, we need to first convert from moles of one substance to moles of the other, and then we can get to grams. So we look at our balanced equation. We've got 2 for our ratio for Ki, and then PbI2 is 1. All right, so now we're at this step. So now we need to get to our final mass. So essentially we'll do the same thing as our second step, so this step right here, except it's just going to be flipped. And again, let your units drive your setup. So we got moles of PbI2 up here. That means we have moles of PbI2 down here. And again, that conversion factor is that 1 mole equals whatever the mass is. Okay. So same thing as before, we'll need to now calculate that mass, which it is 1 mole to whatever that mass is. So we've got PbI2. So iodine was right here, lead right here. So lead is 207.21. And iodine, which notice how I'm putting this in parentheses right here, 126.9045 times 2, because we have 2 of them. And that's going to give us 461.019, which we can round that to 461.02. Okay, and now I know this looks like a lot, but again, we're going to solve for these types of questions exactly the same. So we've got 30 grams times 1 times 1 times 461.02. So again, we're just multiplying everything that's on top. 30 times 1 times 1 times 461.02. Okay, and now we're going to divide by everything that's on the bottom in parentheses. So 166 times 2 times 1, close the parenthesis, and that gives us 41.65. Actually, sorry, 41. It says 41.658, so we'd round that to 41.66. Now, again, I know this probably seems pretty daunting, but again, use your materials, use the stoichiometry map to help you fill in the gaps. And the setup of these problems will always be the same. We're always going to have a given. We might need to do a little calculation like we did in the previous one first, but we just plug in our conversion factors using the information from the balanced equation, using information from the periodic table, using information from the question to convert between each of these different steps. And notice how we kind of have this pattern where we go same unit up here, same unit down here. Next step. Same unit up here, same unit down here. Next step. Same unit up here, same unit down here. Next step, and now we're done. Okay. So my goal in this video is to kind of make this pretty comprehensive. So let's go ahead and, now that we kind of understand the sequence of this, let's go ahead and fill out the rest of our stoichiometry map so we can, using this, we can solve for any combination of these different types of questions. And again, you can use this on our quizzes and tests, so you'll always have this as a resource. Okay, so there are 2 other options for how we can be given information to plug into these equations, and we'll look at example 6 in just a moment. So if we look here, okay, we've got another volume. Okay, so this is going to be liters of a gas that's at STP, aka what we call standard temperature and pressure. Now, what's kind of nice about that is that the conversion factor is really easy for that. It's that 1 mole equals 22.4 liters. So 1 mole equals 22.4 liters. Now, we need to read it carefully because there are going to be times when we're going to have a volume and we're going to be given a certain amount of liters of a gas, and we're going to be trying to solve for it when it's not at STP, or standard temperature and pressure. So when we do that, if you remember back from way back earlier this semester, if you need to, maybe check out some of our recap videos from earlier this semester, or maybe just do a YouTube search for ideal gas law questions. So that's what this is here, PV equals nRT, or PivNert. So if you remember, P is going to equal our pressure, and that's usually going to be in atmospheres. V stands for our volume, So let me zoom this in. So I'm writing a little small here. Okay. Which is usually going to be in liters. N is what we're actually going to need to solve for, because if we remember, N is the number of moles. So for this part, we're actually going to be solving for N to get from here to here. Okay. So R, if we remember correctly, that's our constant. That's going to be 0.08206. Technically, it has a long unit designation, but I'd rather just have you guys take care of the number. And then T is going to stand for the temperature. Now, the trick with the temperature, okay, is that we are going to need to convert to a unit called Kelvin. Which essentially is K there. So the way we do that is that an amount of Kelvin is going to be the degrees in Celsius, except we're just going to add 273 to the degrees Celsius. So if you remember, Kelvin is based on the movement of the molecules, so absolute zero is as cold as it's physically possible. That's when the molecules would actually freeze and would not be vibrating. So to get to that, we just add 273 to whatever the measurement is in Celsius. So for these, we're always going to be given the pressure and the volume. Or sorry, you're going to be given the volume, you're going to be given the pressure, and you're going to be given the temperature, and we're going to need to solve for the N, the number of moles. So you're always going to be given the pressure in atmospheres. You're always going to be given the temperature, which again is in degrees Kelvin. Sorry, will usually be in Celsius or Kelvin, but we'll need to convert into Kelvin here first. All right, so lastly here, real quick, let's kind of get a recap on what this equation looks like. So if we're trying to using this Pivnert equation, and we're trying to solve for N, okay, well, we'll need to do this first before we go and plug into our conversions. So the equation for N is the pressure times the volume divided by our R value times the temperature, which again needs to be in Kelvin. So let's go ahead and plug this in. I know this looks like a lot, and yes, this is a little tricky. I would maybe put a box around this here because this is really all we need to know. And basically, we're just plugging everything in to solve for the number of moles of our given here. So let's go ahead and look at how this would work in practice. Okay. So this question is that we're trying to okay. So now let's go ahead and plug in what we just talked about to this last example here. So here we've got a question asking how many grams of sodium are required to react completely with 2.5 liters of Cl2 gas held at 5 atmospheres and negative 75 degrees Celsius. So we have atmospheres. That should be a big red flag. So we know we're going to be dealing with this part right here. So again, all we really need to do is just plug into this equation to solve for the given number of moles. Okay, so we're given all this information here, and then the temperature right there. Okay. Now, we need to keep in mind that the temperature is in degrees Celsius, so we will need to convert this into Kelvin. So we've got negative 75 degrees Celsius plus 273 for Kelvin. So negative 75 plus 273 gives us 198 Kelvin. Okay, so that is our temperature. Okay, we have our volume right here, 2.5 liters. We have our atmosphere, our pressure here. So now we need to solve for N. So remember, we're using this equation right here. N equals PV over RT. So we solve for that first. So PV, so that's the pressure, so 5 atmospheres times the volume, which was 2.5 liters, divided by RT, so that was, again, from here, your R value is 0.08206. And then multiply that by our temperature, which was 198 Kelvin. And again, the identity of our substance is Cl2 here. So we go and plug that in. So 5 times 2.5. Again, I'd hit enter. And then divided by 0.08206 times 198. Close the parenthesis for everything that's on the bottom. And that gives us a 0.769, which we can round that to 0.77. And that's moles of Cl2. So that's the substance that we had here. Okay, so now we are at given number of moles. So now we need to convert from given moles to unknown moles. So again, we've got moles of Cl2 up top. We need moles of Cl2 down here. Then we've got moles of, we're trying to get to Na up top, and pardon the bell, it's about to ring. And I've noticed I forgot to balance this out, so let's balance the equation real quick. So we've got Cl2 here, we need a 2 right there. So the ratio between the two here for chlorine, or I should say chlorine gas, Cl2 is 1 to 2 for sodium there. All right, so right now we're here. Okay, so now we need to go from unknown moles to our mass of moles. Mass of our unknown, I should say. So if we remember, the conversion factor for that is going to be 1 mole equals blank, or the mass from the periodic table in grams. Okay, so sodium here, easy enough. We've only got one of them. So sodium is 22.98976, which we can round that to 22.99. Oh boy, oops, sorry, ignore me here. Forgot to put moles of Na down there, because you remember we've got moles of Na up here. So we need moles of Na down here. So then we'll put 22.99 grams of Na up top there. Now we'll solve this the exact same way as we've done in the past. So 0.77 times 2 times 22.9. And then we would divide by 1 times 1, which would give us the same answer. So that'll be 35.41 grams of Na for our final answer there. Okay. So I know our heads might be spinning a little bit, and this is going to be something that we're going to build on over the course of the next couple weeks. So don't panic if you're still kind of scratching your head. We will go through some more practice. The last thing I'd like to do, though, is I would like to help us finish this out here. So like I said earlier, what is kind of nice with this mole map is that it's a mirror of both sides. So all of these inputs that we had going from the given to the number of moles are going to be the exact same process to get to each of those outputs for each of those unknown units. All right, so in order to put the mirror image on both sides, we're just going to basically transcribe what we have over here to this side here. So we're going to make them the exact same. I'm going to abbreviate the stuff on this side just so we don't have to write everything that we have over here, but we do want to write each of our conversion factors, what we're going to be plugging into our stoichiometry equations. So if we have another volume, okay, but we're given a molarity, so if we're trying to solve for a volume with a concentration, right, we're going to use the exact same kind of equation here. So we're trying to solve for the amount of liters, okay? So we're going to plug that in. So it'll be 1 liter equals blank moles. So that's what we will have as our previous component here from the unknown moles. So we're going to use, again, molarity here. Okay. So big M equals molarity. Okay. And then this right here, so we're going to have same thing as we have on this side. So if we have the volume, so liters of a gas at STP, so standard temperature and pressure again. So it's going to be 1 mole equals 22.4 liters. It's going to be our conversion factor there. And then lastly, okay, we're going to use our Pivnert equation. Again, I'm not going to rewrite all this stuff down here, but we just know that we're going to use PV equals nRT, except instead we're going to be solving for the volume. So our equation is going to be a little bit different. So we're going to solve for V. And again, remember that the R value is going to be 0.08206. Okay. So again, we're trying to solve for the volume of a gas not at STP. Okay. So whenever we're trying to solve for this bottom one, I'm going to give you the pressure. So again, that's a value in atmospheres, and the temperature. So again, you might still need to do those conversions, same as we did before, in order to solve for that and plug into this equation. So essentially, the part that we'll solve for separately here is we'll have a volume that we're trying to solve for. For this part, we have a number of moles. That's our N value. Okay. So that's going to be N times R. So our 0.08206 times the temperature divided by the pressure. So that outlines each of the different possible combinations of what we can have with this mole map. So we'll periodically be practicing this throughout this unit, but hopefully this was helpful. And if you have any questions, always don't hesitate to reach out. And I have some tutorial videos posted on Google Classroom to help you as well. So I hope that was helpful, and we'll see you guys soon.